Good afternoon. I'm Alistair Reed from Norfolk College. I'm pleased very much to be able to introduce Geoff Loftus to the behavior analysis community. Geoff has made truly impressive contributions to science in a wide variety of research areas. So he and his research will be very well known to many of you. Geoff received his BA degree from Brown University in experimental psychology. He received his PhD from Stanford in 1971, also in experimental psychology, under the supervision of Richard Atkinson. He's been at the University of Washington since 1972. He's taken sabbatical leave to work for the National Institute of Aging and at MIT. He's received about $2.5 million in grant support over the years, working in the areas of eye fixations, short-term memory, picture memory, visual perception, and attention. Some of Geoff's impact has been quite ironic. While he was a visiting professor at MIT in 1995, he managed to convince the Department of Brain and Cognitive Sciences to buy an LCD projector for teaching, thereby helping to wean MIT from the blackboard culture to which it had been wedded since its founding. Somehow I would have thought that a school with a name like MIT would be quite familiar with this technology. Geoff has published scores of articles and 6 books in an incredible array of topics: aviation, computer simulation, eyewitness identification, forgetting curves, mathematical psychology, verbal memory, visual memory, and many others. But I think one of his most important contributions to science has been in the area highly related to behavior analysis. The issue is, how do we form conclusions from our data? What part of our science could be more fundamental than that? We carefully design our experiments, we control extraneous variables, we try to make inferences from our data. What is our justification for these inferences? Behavior analysis has a long history of being concerned with the appropriateness or adequacy of statistical tests. In our journals, in experimental analysis of behavior vary considerably from their expectations of our statistical analysis and data presentation. For this reason, please join me in welcoming Geoff Loftus as he presents hypothesis testing, curse or abomination.
Thanks. It's, let's see, can we turn this off so we don't get feedback? Maybe it's already off. Anyway, it's an honor to be invited here to give a preeminent tutorial. I'm kind of hoping that sometime I'll be able to give an eminent tutorial, and maybe even after that a post-eminent tutorial, but for today we'll just do preeminent. I want to start with one caveat. There are 3 groups within psychology that are probably those that least need to hear this message. One are the vision scientists who go to ARVO, and the other 2 are the very 2 groups that are represented here today. So I have a feeling that I'm going to be sort of preaching to the choir here, but what the heck? It's the end of the day, so I guess we can all just sort of kick back and congratulate ourselves for correct thinking and how to do data analysis, and maybe smirk a little bit at most other areas of psychology that don't. I do have some relevant articles to which I could guide you. They're downloadable, so please feel free to email me. Some of them are mostly whines and complaints. Others are mostly solutions, but you're welcome to all of them, plus others. So let me briefly describe the process of hypothesis testing. Won't come as any news to anyone. So the basic unit of standard hypothesis testing is you ask a simple question, like, is some null hypothesis true? You get a simple answer. Technically, this answer is either no or we can't tell. In fact, often it's just no or yes, and I'll come back to that in a little bit. Based on a series of such binary decisions, one tries to make sense of a data set, no matter how complex this data set is. Now, you're all trained psychologists, and you've probably used your training to infer from my title that I don't really like this as a way of analyzing data. I certainly don't think that it is optimal. It's been around for a long time, as all of you know. but I think it's left our science, or not your science, but much of psychology, plus much of many other sciences in sort of methodological and theoretical cul-de-sacs. Hypothesis testing, as I suggested a second ago, has a fairly lengthy historical role. Here's a paraphrase of a statement made by Arthur Melton, the venerable Arthur Melton, in 1962 when he stepped down as editor of Journal of Experimental Psychology. He essentially said manuscripts that do not reject the null hypothesis are almost never published, results significant only at the 0.05 level are barely acceptable, whereas those significant at the 0.01 level have deserved a place in the journal. Well, there's a reason to do hypothesis testing. The more hypothesis testing you do, the more likely it is that you'll get tenure. Not everybody took that view. Here's David Grant, also in 1972, writing in Psychological Review. He said, in view of our long-term strategy of improving our theories, our statistical tactics can be greatly improved. Yes, by shifting emphasis away from overall hypothesis testing in the direction of statistical estimation. For example, when testing a presumed null pretreatment difference between two groups, an investigator would do better to obtain a confidence interval for the pretreatment difference. If the interval is small and includes 0, the investigator is on fairly safe ground. But if the interval is large, even though it includes 0, it's immediately apparent that the situation is more serious. In both cases, the null hypothesis would have been acceptable. Well, that seems like a very sensible way of looking at things. And indeed, other people have made the similar point, or similar points over the years. Here's just a fairly small sample of some of the people who have written talking about problems with hypothesis testing. The problem is that hypothesis testing is so ingrained that these don't generally seem to do any good. So somebody will come along and they'll write an article on why hypothesis testing is bad, and people read it and they'll say, oh yeah, that's a good point. But then somehow the point never sticks. It just sort of dissolves away in the vast acid bath of existing experimental orthodoxy, and on we go. So who won between, say, Grant or Melton and all those other people? Well, hypothesis testing is still used in over 95% of research reports in psychological journals. So we have still got a long way to go in terms of getting the message across. I am happy to say that things seem to be changing a little bit. Over the past 5 years or so, there have been task forces formed in places like the APA and the APS, and they're having possibly some effect. I'm not sure. What do journal editors think about hypothesis testing? About 5 years ago, I emailed a survey to all important editors and associate editors of major psychology journals who met the following very strict scientific criteria. First, the name of their journal came to my mind within about 30 seconds of my deciding to do the survey. Second, I either knew who the editors were or happened to have a copy of the journal around so I could find out. And lastly, I happened to have their email addresses handy. Here's what I asked, or one of the questions I asked. Do you think hypothesis testing should be used as the major data analysis technique? Always, usually, sometimes, occasionally, or never. Here are the results of that question in that survey. As you can see, the modal answer was usually, so journal editors were still pretty wedded to the process of hypothesis testing. A large number of people said sometimes, one occasionally, one never. That was the editor of Memory and Cognition, who happened to be me at the time. I included myself in the survey. But still, it doesn't seem that, from this survey anyway, that hypothesis testing is going to go away anytime soon. And a casual reading of most of the journals, at least the journals in my own field of cognition, seems to verify that conclusion, alas. So the goals of this talk are twofold. The first is to articulate why I'm disenchanted with hypothesis testing as the major means of transiting from data to conclusions. As I said, this is not original. Many people have made all of the points that I'm going to make at one time or another. And to suggest several alternative techniques for extracting more insight and understanding from a data set. So let me start by talking about what's wrong with hypothesis testing, and I've organized my complaints into 6 problems that I'll go through very briefly. The first is that hypothesis testing revolves around the testing of a null hypothesis that's rarely true. So, for example, and I apologize, I'm using here an example from my own field. Suppose you have a digit recall task in which there are 5 exposure durations ranging, say, from 10 to 100 milliseconds. These numbers don't really matter all that much. You have a performance measure like proportion recalled digits or something like that. And then, if you want to do hypothesis testing, you have a null hypothesis, which essentially is that, in terms of population means, the 5 population means corresponding to the 5 conditions are equal to one another, where equal really does mean equal. I mean, no fair cheating and saying that they're about equal to one another, because then either the logic of hypothesis testing falls apart, or you have to twiddle with it a little bit to precisely define what you mean by about equal. That actually has been done. People have used the concept of a null interval, but in my experience, I've never ever seen it actually put into practice. Well, such a null hypothesis that these 5 population means or any other population means can't be literally true. We all know that in living organisms, as in most of the universe, everything affects everything else, at least to some degree. And I know everybody can come up with a counterexample somewhere, somehow, but basically, that's true. Null hypotheses can't be true. So what do you really find out as the result of hypothesis testing? Why, if you know the null hypothesis is false to begin with, you can't find out anything that you didn't already know. What you do find out is whether your experiment had enough statistical power to detect whatever effect must have been there to begin with. Let me just provide you with an analogy here to drive home what I mean. Suppose that an astronomer comes along and tells us that on the basis of the color of the moon, we can reject, at a 0.01 level, let's say, the null hypothesis that the moon is made of green cheese. Well, we would all say, all right, you know, we can accept that, but so what? We all knew that the moon was made out of green cheese to begin with, and probably we would begin to think that the astronomer who made this statement was a little bit daffy. Strangely enough, legions of psychologists who make analogous conclusions are continually thought to be entirely sane. I couldn't resist sort of driving this a little further. As many of you probably know from having asked your students and possibly your colleagues, there's a common misconception of hypothesis testing. If you ask somebody what it means to say that you've rejected a null hypothesis at the 5% level, one of the many interesting responses that you'll get is that people say an error will be made in 5% of all experiments in which the null hypothesis is rejected at the 0.05 level. That's not, of course, true, but a lot of people will tell you if it's true if you ask them. The extension of the analogy, of course, will be that 5% of all planets for which the moon is made of green cheese hypothesis is rejected actually are made of green cheese. All right. The second problem I call the multi-degrees of freedom problem. So suppose you do an experiment, a fairly complex experiment. I guess this is a 6x3 design here. This experiment was presumably carried out to test some prediction, and the prediction is usually, in my experience, of the form there will be an interaction, fairly vague prediction here. And the data indicate that, sure enough, there is an interaction. And the conclusion is that the prediction is confirmed. And that's pretty much the end of the story. Now, I know there are lots of ways, again, using hypothesis testing, of disentangling various potential data patterns so you could hone in on the interaction that you actually have in mind. Sometimes these are used, sometimes they're not. Many times I've read in journal articles something that really corresponds just about to that. You have a conclusion that's essentially a 1 degree of freedom conclusion, but is based on a multi-degree of freedom data set. The third problem with hypothesis testing is lack of attention to statistical power. hypothesis testing has come to revolve critically around the avoidance of type 1 errors, as we all know. There is this thing in hypothesis testing called a type 2 error, but issues of type 2 errors and the related measurement of power are largely ignored in data analysis. Now, this, of course, is because within the context of hypothesis testing, knowing about power and beta requires having some quantitative alternative hypothesis, and quantitative alternative hypotheses are very much lacking in most of the field of psychology. But nevertheless, it's important to understand power and the power of your experiment somehow or another. Lack of considerations involving power become particularly worrisome when, and this again happens many times, when an investigator implicitly accepts a null hypothesis without presenting any power analysis. And I'll have more to say about this in a little bit. The fourth problem with hypothesis testing has to do with what I've referred to as the sanctity of the 0.05 level with respect to conclusions that get made about effects on the one hand versus non-effects on the other hand. So just to dwell on this for a moment, often you see significant, non-significant, or significant declarations that are made in the results section of some paper. So if P, for example, were 0.0499, the effect would be declared significant, whereas if the effect were 0.0501, it would be declared to be non-significant. Now, we're rational human beings. We know that a data set that produced this result and a data set that produced this result are very, very similar to one another. But of course, this similarity does not follow through in terms of the conclusions made from the experiment. Instead, the significant or non-significant conclusion or finding from the results section morphs into the corresponding but misleading conclusions about effects or non-effects in the discussion section. We're all taught from our first introductory psychology course that when you have a non-significant effect, you're not supposed to accept a null hypothesis. You're just supposed to conclude that you don't really have enough evidence to make any conclusion at all. But to paraphrase Alicia Silverstone in Clueless, people have a great deal of difficulty. They're just loath to make conclusions that are both complicated and weak, like we don't have enough data to make any conclusions about what's going on here. So instead what happens is that whereas a significant effect, a significant result turns into the effect exists, that's okay, a non-significant effect somehow in the discussion section and for the remainder of any discussion of whatever experiment is under consideration here turns into the effect doesn't exist, which often leads to much confusion later on down the road. I can't tell you how many times I've traced a sequence of events in which somebody does an experiment, they find a significant result. Somebody replicates the experiment, they don't find a non-significant result. Everybody becomes all aflutter because now we have a failure to replicate, and much time and effort is spent scouring the method sections of these two experiments to try to figure out what led to this failure to replicate. And basically, it's just accepting a null hypothesis when you shouldn't be doing it. The last problem I want to briefly discuss I call the off-the-shelf assumptions problem. And what I mean by this is that the process of hypothesis testing forces, or at least nudges, theory construction into what I've called sort of a fairy tale land where all kinds of things are true. Variances are unaffected by treatments. Variables are all normally distributed. Monotonic relations are all linear relations. And all results are reduced to binary statements about the presence or absence of main and interaction effects within a linear model. Now, it's not really so much the validity of these assumptions that I am concerned with. Rather, it's that these assumptions all sort of determine what kind of theories get constructed. The data analysis method sort of wags the theory construction dog, and we wind up with a whole bunch of models that are all constructed within the context of the general linear model, and other perhaps more realistic and interesting models are never thought of to begin with. In other words, off-the-shelf assumptions produce off-the-shelf theory. This morning, I was sitting next to, I was watching Peter Colleen, and he suggested that I might want to talk somewhere in my talk about forgetting, since Jeff White, the previous speaker, talked about forgetting. And ever compliant, I raced up to my hotel room. One of the advantages of doing a presentation on PowerPoint is that you can obsess about what you're going to say and add to the talk right up to the very last moment. So here's an example of what I mean when I say that all the assumptions of hypothesis testing in conjunction with the linear model sort of determine theory construction. So suppose you have a hypothesis that original learning doesn't affect forgetting rate. This is something that I've written about, and I can send you the articles if you want. And without going into all the details, because that really isn't the point of this talk, the prediction is that forgetting curves are horizontally parallel. In other words, if you plot a forgetting curve of high learning and low learning, the horizontal distance between them ought to be parallel. That's the prediction of the proposition that original learning doesn't affect forgetting rate. But in my business of cognition, whenever I've seen these kinds of experiments, well, not always, excuse me, John Wickston, they're analyzed using a traditional analysis of variance, where you find an interaction. This distance is greater than this distance down here. But the interaction that you see in the analysis of variance is completely uninteresting with respect to what you really presume to be happening. It is irrelevant, in other words, to the prediction made by this hypothesis. So let's see. Oh, one other problem. The results of hypothesis testing tell you little about the validity of the null hypothesis. So again, this is illogic that most of us have probably bumped into at one time or another. Again, what we all learn in our introductory statistics course is that a result is that the probability of some data, given the null hypothesis, is small. Let's say less than 0.05. But the conclusion is that we reject the null hypothesis. These are the words that we use when we get a result like that one up there. We say we reject the null hypothesis. Now, in everyday normal language, what would it mean to reject the null hypothesis? It means to conclude, given the data, that the null hypothesis is incorrect. That's what rejecting the null hypothesis means. So in other words, implicitly, many people come to believe that the 0.05 level refers to the opposite conditional probability. Rejecting the null hypothesis means concluding that the probability of the null hypothesis, given the data, is small. And of course, the problem is that there's no reason to conclude this based on this. Now, once upon a time, when I was giving this talk at one of those Boston area schools, I think it was Harvard, I made up an analogy to illustrate what I mean by that. And let me try this out on you. Suppose it's known that Boston drivers stop at stop signs less than 5% of the time. So now let's suppose an incident occurs. A driver on the streets of Boston, driving a car with Massachusetts plates and a Go Red Sox bumper sticker, does stop at a stop sign. following which he runs down a pedestrian and then drives away, except for the stopping at a stop sign. This happens a lot, actually, in the city of Boston, my hometown. So suppose that based on eyewitness testimony, plus physical evidence like paint scraping matches and stuff like that, a Boston resident is arrested and put on trial for the hit and run accident. Now suppose that the defense lawyer has taken a course in statistics and makes the following argument. The defense lawyer says, given the culprit is a Boston driver, the probability is less than 5% that he would have stopped at a stop sign. Because the culprit did stop at a stop sign, the jury should reject the hypothesis that he was a Boston driver. Therefore, the jury should conclude that the defendant, who was a Boston driver, was not the culprit. That's it, Your Honor. What do you think about that? So, would you buy this argument if you were on the jury? Well, the answer is that of course you wouldn't. It's ridiculous. The stop sign issue is virtually irrelevant in the grand scheme of things, given all the evidence the Boston driver was probably the culprit. The logic here is that we have some knowledge, namely that the probability that somebody stopped at a stop sign, given that he's a Boston driver, is less than 0.05. The defense lawyer wants you to conclude that this means that the probability that the opposite probability, the probability that he was a Boston driver, given that he stopped at a stop sign, is low. But jurors, like sensible people they are, realize that this does not imply that. The logic is perfectly reasonable, in other words. Now let's look at a parallel scientific situation. This I read, this is by Berger and Barry, an American psychologist. It's not mine originally. Suppose an investigator asks, does vitamin C decrease the severity of colds? And in a properly carried out double-blind experiment, everything all copacetic, 16 subjects are sometimes given vitamin C when they have a cold, and other times are given a placebo. And subjects in the experiment are asked to rate the severity of their cold in both situations. Suppose that 11 of the 16 subjects have lower cold severity ratings with vitamin C than with the placebo, so this is statistically significant by a sign test, p less than 0.05 and all that. So imagine that the investigator writes up this result, and in his manuscript, the investigator makes the standard statistical argument, which is that given that vitamin C doesn't affect cold severity, the probability of this extreme in outcome is less than 0.05. Therefore, one should reject the null hypothesis that vitamin C doesn't affect cold severity, and so accordingly one should conclude that vitamin C decreases cold severity. So the question is, would you buy this argument if you were a journal editor? And the typical answer is, of course. By scientific and statistical tradition, a finding of p less than 0.05 is sufficient to reject the null hypothesis of no vitamin C effect and conclude that vitamin C effect does exist. So the logic here is, as I said before, the probability of the data given that the null hypothesis is less than 0.05. The conclusion is that somehow this must mean that probability of the null hypothesis given the data is low. In fact, there's no logical reason for making this conclusion from this finding. I should say, as an aside, that these two conditional probabilities are probably related to one another. After all, they have the same numerator in the equations for them. But nevertheless, it means that this sacred value of 0.05 on which careers rise or fall doesn't refer to anything that you should be directly interested in making your conclusions. Okay, so now let me talk about what are some alternatives to hypothesis testing. And once again, I'm sure I'm not going to be bringing any new news, at least to this group. All I'll do is to sort of organize my thoughts in a coherent fashion. So here are 5 possible alternatives. First is graphing the data so we can see what it looks like. Second, using error bars. Third, reduce the number of factors in your design using some a priori model. Fourth, make use of planned comparisons. And fifth, generate a quantitative theory that you'd like to confirm as opposed to a typical null hypothesis that you'd like to reject. So let me go through these suggestions. Let's suppose that Jennifer Loeb, a cognitive psychologist, is studying memory for visual materials. Her task involves memory for dots in a matrix like this one. So in this task, she varies a couple of things: stimulus, exposure, duration. She has people either engage or not engage in verbal encoding, and suppose that the locational uncertainty of the dots in the matrix are either high or low. And the dependent variable is just the number of dots you get correct in the correct positions. Suppose that Loeb's theory makes the following predictions: that the performance measure increases linearly with exposure duration, that the slope should be higher with verbal than with no verbal encoding, and that the slope should be higher with low than with high uncertainty. Now, once again, having served 4 years as memory cognition editor, I saw an awful lot of result sections that would look like this. There would be a table that would provide numbers corresponding to all, let's see, 1, 2, 3, 4, 5, 6, 7, 8 times 4, 32 conditions here with a whole bunch of numbers in them. And associated with this would be text that goes in 8 by 2 by 2 repeated measures and over reveal the main effect of it. And this stuff goes on sometimes for pages. It's unbelievably dreary to read. Now, it's always astonished me. It astonishes me even more than when I go to vision conferences and the text is all either blurred or too small to read. We're psychologists. We should know that human beings are not constructed to be able to assimilate big batches of numbers like this. And yet, there they come routinely, one table after another. There used to be an excuse for it, which was that making figures was really hard to do. There's obviously that excuse doesn't hold anymore. It's just as easy, in fact, easier generally, to make a figure than to make a table. So plotting data rather than putting it in the form of tables is my first suggestion. Again, this might seem like second nature to all of you, but it's shocking how many people in our field it isn't second nature to. Nevertheless, it's really true that a picture is worth 1,000 words or 1,000 numbers, and here are some of the pictures. The second suggestion is to provide error bars around whatever sample statistics are critical for conclusions. It's been my subjective feeling that I'm seeing error bars in more and more articles and more talks these days, but I can never figure out why people just don't put them in routinely. Here's Loeb's data. So we look at the sample means here, and they give us a pretty good idea of what's going on. The only thing missing here is any measure of variability. We don't know how good these sample means that we're viewing are as a reflection of the underlying pattern of population means in which we're presumably interested. All you have to do is add error bars, and basically, as far as I'm concerned, that's all you really need to do in order to display all the information in that formerly tabular data. Now, a particularly good time to use error bars is when you do want to accept some null hypothesis for all intents and purposes. And the reason for that, of course, is that, as I mentioned earlier, and as I'm sure you're all aware, statistical power is especially important under such circumstances. So let me give you another hypothetical example. Suppose that a guy named Jonathan Sanders, a clinical psychologist, is studying treatments for agoraphobia. Sanders' agoraphobia therapy experiment, he carries out an experiment to test several possible treatments for agoraphobia. Here are his procedure and design. He has two groups, let's say. One is what I'll call the standard treatment, the one normally used to deal with agoraphobia. Another, let's say, is a treatment that he's invented that's presumably cheaper and easier than the standard treatment. So all else being equal, you'd want to use his. The dependent variable, let's say, is rated agoraphobia on a 1 to 10 scale a year after the treatment. And Sanders' prediction, which is to say his hope, is that there'll be no difference between the two conditions, because if that turns out to be the case, as I said, his treatment being cheaper and easier would be the preferred one. Now, here's a not that uncommon way of reporting results in an experiment like this. the difference between the standard and the standard treatment group was not statistically significant. That should say P greater than 0.05, okay? That's what you see, honest to God. I mean, you may not have, but I do all the time, and it's kind of shocking because the immediate thing that you want to know, of course, is what's the meaning of the term not statistically significant? Very generally, two possibilities are, first, that there's low power in this experiment, in which case results are not very meaningful, and second, that there's high power, in which case the results are meaningful. As I said earlier, it's very tough in most experiments to really get a measure of power in the hypothesis testing sense of it. But you can look at general power just by looking at confidence intervals or error bars in general. So low power is reflected by large error bars, whereas high power is reflected by small error bars. So this kind of a picture would give the consumer of these data sufficient information to make a decision about what's going on. If you looked at this situation, you would say, okay, the null hypothesis isn't rejected, and what's more, we have no idea really what the relation is between population means in these two treatments. Whereas if there is high power, it's still, of course, true that you can't logically accept the null hypothesis, but what you can conclude is that whatever difference between the two treatments does actually exist is really small. And so for all intents and purposes, in other words, for any as far as any practical implications are concerned, you may as well go ahead and accept the null hypothesis. It's reasonable in this situation, but not reasonable up here. Speaking of error bars, I included another question on my survey. Do you think error bars should be plotted always, usually, sometimes, occasionally, or never? Most people said usually. I didn't actually know why they didn't think it should be plotted always, which got a fairly low rating. There was me and one other person, Roddy Rodiger, actually, who said they thought they should always be plotted. Most people, as I said, thought usually. Some people thought sometimes, and thankfully nobody said never. The third possibility is to reduce the number of factors in your design using some a priori model. In other words, once you're convinced that some model is reasonably accurate or describes your data reasonably well, you can use some theoretical parameter that you get from the model as your dependent variable. So just to give a quick example of this, in the Loeb data I described earlier, the focus here is on slopes. If we can be pretty convinced, based on our a priori knowledge, that linear functions are a reasonable way of designing these slopes, then we can just look at the slopes themselves as our main dependent variable and plot error bars around them. The fourth alternative is to make use of planned comparisons. Planned comparisons, which usually take the form of contrasts, is something that I learned about in graduate school from the late Merrill Carlsmith, and I thought they were great. If you're committed to hypothesis testing in particular, they're a great way of dealing with understanding what the pattern is of a set of data. I've been amazed at how little use of planned comparisons I've seen in the intervening 30-odd years since I learned about them. Very briefly, to carry out a planned comparison, you need some quantitative hypothesis about the underlying pattern of population means for the various conditions in some experiment. This is particularly useful if the experiment is a complex one involving lots of conditions. You then generate weights, which are numbers, one per condition, that correspond to the hypothesized pattern of means. And then you essentially compute the over-condition correlation between the weights that you've generated and the sample means themselves. And you get a lot of information from planned comparisons. You, for example, get the percent of between condition variance accounted for by the hypothesis. That's the Pearson R squared between the weights and the means. You get, of course, the percent of between condition variance not accounted for by the hypothesis. you can test the proposition, that is the null hypothesis, that the underlying r squared is 0. That is that the hypothesis accounts for none of the underlying variance in the population means. And you can test the proposition that it's sufficient to explain everything, that it accounts for 100%. These are still hypothesis testing procedures, but if you feel you have to carry out some sort of hypothesis testing procedures, I tell my students at least do it this way, because it's sort of useful. It's not completely unuseful. My final suggestion is to generate a quantitative model to summarize data. And I'm sure you're all thinking, hello, this is SQAB. We're in Peter Colleen territory here. I shouldn't really have to describe or justify this kind of technique. It's been described amply in the previous talks, so I won't go into it any further. Except to say that I've always reflected on the stark contrast between conclusion by p-value on the one hand, in other words, the way you make conclusions using traditional hypothesis testing, versus conclusion by root mean square error, or whatever other means you want to use to evaluate the goodness of your quantitative model. Conclusion by p-value tells you that something that you're not interested in isn't true, whereas conclusion by root mean square error tells you something that you are interested in is reasonable as a way of accounting for your data. And I just can't imagine that anybody would prefer this over this, but 90% of the world does. Go figure. So let me make some conclusions here. There's a variety of reasons that I've talked about in this talk and many other variants of this talk, and many articles that I've written, and has been talked about in many articles that many other people have written and have been taken up by task forces here and there and generally discussed but not strongly implemented. Anyway, that hypothesis testing, as typically used, is quite barren as a means of transiting from data to conclusions. I've talked about some techniques to supplement or replace standard hypothesis testing. They are, when the data are at all complicated, graph them rather than presenting them in tables, put error bars around important sample statistics, use a theoretical parameter rather than the raw data as the dependent variable, particularly when you've got a theory that you believe in, make use of planned comparisons, generate quantitative models. And these techniques are designed to assist us in the ultimate goal of understanding what some data set is trying to tell us. Now, before I conclude, let me just make one more brief set of remarks. I've occasionally given a talk, and I have written a paper, entitled something like the following: Why Psychology Will Not Be a Real Science Until the Way We Change the Way We Think About Data Analysis. And I hope that the arguments that I've made in this talk will provide you clues as to why I believe this to be true. I use the term real science sort of loosely. I believe, however, that a fundamental criterion of a real science is that its primary data analysis technique provides genuine insight into whatever phenomenon the investigator has set out to investigate. And the primary data analysis technique within psychology and many other social sciences and many other sciences in general, namely hypothesis testing, does not, as I've tried to demonstrate, meet this criterion. Now, admittedly, acquisition of insight is not simple. In the social sciences, where we're cursed with an enormous number of uncontrolled variables and hence error variance that has to be accounted for somehow. And any science is supposed to be able to deal with this kind of thing, with error variance that is inevitable in any experiment, in some objective fashion. I believe that historically, social scientists have embraced hypothesis testing procedures because they provide the appearance of objectivity. Now, hypothesis testing procedures may indeed be objective in the sense that they provide universal and relatively unambiguous rules for making a scientific decision. If p is less than 0.05, you reject the null hypothesis. If it's not, you don't. But objectivity is, alas, not sufficient for insight. I believe that these rules for hypothesis testing provide not real insight, but only the illusion of insight, which I think is undeniably worse than having no insight at all. Thanks. Yeah.
Why do you think that the practice remains so strong after all this sort of talks and writings about this?
It's a damn good question. The question is, why is it still around? Why is it so pervasive? I think the answer is inertia. And there's a kind of a chicken and egg problem here. So things aren't really going to change until statistics classes have changed, until statistics books have changed, until editorial policy has changed, until policies of places like the APA have changed. But none of that is going to happen until people start changing their techniques to show that there's actually value in alternatives to hypothesis testing, and until people start feeling comfortable with them. And that's a very hard problem to solve. As I said, I think that in the past 10 years, there's been an increasingly rapid drumbeat of discontent with hypothesis testing, and I actually believe that it's having some effect. Although I regret to say that when I was editor of Memory and Cognition in the early and mid '90s, I wrote an editorial saying that hypothesis testing will not be really shouldn't be used as the major data analysis technique. That's why I took on this odious job to begin with. I thought I could change the world, and guess what? I couldn't. Manuscripts kept pouring in using hypothesis testing. I can't tell you how many confidence intervals I computed for people and told them to publish them. And so recently there are some people in Australia, Sue Finch and Alan, I think his name is Cummings, who investigated what the effect this editorial policy in memory and cognition, what effect it really had. And it turned out that the results were fairly woeful. Not only did it not have that much of an effect when I was actually editor, but once I stopped being editor, whatever little progress had been made evaporated with the incoming new editor. So that's the bad news. I think that things are changing. I think that technology, the ability to generate graphs, to do the kind of exploratory data analysis that's vastly more interesting that was described earlier, to compute confidence intervals and things like that are all helping. But man, we got a long way to go. Yeah, Russ. I can't not ask Russ. Russ taught me my first introductory statistics course when I was an undergraduate.
I apologize.
I knew even then that there was something wrong with hypothesis testing.
You mentioned something about objectivity of standards. I'm always worried about people's personalities affecting their conclusions and comparing how one evaluates. Do I have a fact here worth communicating? And use that way as a lower standard. And should I say anything more to you about this fact I have here? It gives us a common way of doing it, which is obviously far from sufficient, but it is something to do to just go on with the conversation. In contrast, I was thinking of Randy Grace's talk on how we evaluate a theory. So we've got percentage of variance accounted for, but suppose it's very low. 62% working on, but some people. Can we go on? Of course, because we've got so many other criteria too, and they would make up for it. So my question is, what makes up for the p-value of 0.50?
That's a good question. And I agree that there's a lot of subjectivity in interpretation of data in general. And I take, I guess, what's sort of an unusually strong view on this, which is to say that we just have to deal with the subjectivity. Subjectivity is going to be there in any science that has noise in it, no matter what data analysis technique we use. So we have this hypothesis testing technique in the 0.05 that we're wedded to, and great, that filters out the real findings from the non-real findings. But nevertheless, as we all know, there's a huge amount of subjectivity in how we interpret a set of data. You publish a data set, and people will argue forever about what it means this or whether it means that. Hypothesis testing doesn't help at all. And as I said in my last set of comments, I think that one of the real problems, one of the most insidious problems with hypothesis testing is that it provides the illusion that everything's okay. It's this false security blanket that makes us think, oh, we got this objective procedure for doing things, and so we don't have to worry. Well, we do. And we're always going to be subjective in our interpretation of data to one degree or another. The more noise we have, the more subjective we're going to be. And I think we just need to admit that and say, you got to look at a data set. Here's a data set, here are the sample means, here's the standard deviation, here are the error bars, and here's the conclusion that I make. You disagree, you don't agree. You want to argue, we'll argue. But, you want to go do another experiment, go do another experiment. And on we go. But nevertheless, the subjectivity is going to be there, and what the hell? I think we just need to have it out in the open. Yeah, John.
A couple of points. I think it's no accident that this methodology arose in agriculture, where the issue was, is this fertilizer better than that fertilizer? Although you have to make a policy decision, it seems to be perfectly appropriate. I mean, the vitamin C example, if you're going to make a decision that you're going to give vitamin C or not to these people, and you get a result, you say, well, 5%, okay, on balance, it's cheap, probably we should do it. Okay? But that has nothing to do with science. That's part of the problem. It has nothing to do with science. So that's one point. The second point, and I'd like your reaction to this.
I'll give you my reaction to the first point, too.
But the second point is, if in fact the convention were not 5%, but 1%, if it were 1%, I don't think it would be a problem, actually. For one thing, it would cut down the publication rate enormously. You wouldn't have a lot of this stuff to worry about, okay? So my question to you is, what do you think of that? What do you think as a method of attacking this horrendous procedure that is so universal? We should say, well, we don't object to this procedure, but by golly, it would be 1%.
What was your first part of the question? Oh, right. Actually, they're both, I guess my answer to both of them is the same. And, John, I respect you a lot, but I just disagree with the implication of your questions that hypothesis testing is the slightest bit useful to begin with.
Even for policy, you don't think it's even useful?
Yeah, I think you can take exactly the same data and view it and give it to policymakers in a very different way. So you're going to go up to a set of congressmen or a committee or something like that, a congressional committee, let's say, and you're going to say, based on this statistical result, we need to make policy. Now the question is, what would be more useful? Educating them with respect to this convoluted process of hypothesis testing and then handing them a p-value, or saying, here is the mean cold rating when you have the vitamin C, and here's the mean with the placebo, and here are the confidence ratings around them, and you can briefly tell what confidence ratings, or confidence intervals, are all about. I believe that this latter procedure, where you just present the data points or present a mean difference, with confidence interval around it, is just much more straightforward. It's just much easier to present. It's just easier for other people to understand, particularly lay people, than, to present this convoluted hypothesis test, misleading hypothesis testing result. So I don't believe that. I don't believe that increasing the probability, the decreasing the p-value to 0.01 as a standard is really going to solve the fundamental problem. It might wipe out a lot of manuscripts, but it's still going to place the emphasis in completely the wrong place, and it would give us the illusion once again that we've solved the problem where really we haven't.
I would like to compliment a writer of a statistics book coming here and trying to persuade Auckland conditioners not to use statistics.
Isn't it didn't be, you confirmed my memory that B.F. Skinner actually said something like, if you need statistics, it's junk data. Or that's my memory of it. It might have been.
Like, no one comes to a circus to see a dog jump through a hoop statistically more often than chance. I have two questions, as long as I have the floor. Both brief. One is, are you bothered by Eske's point about confidence intervals not really being about true population mean, but only about the sample estimate? Is that a big problem or not? And the other is, what would you tell Ray Nickerson, another journal editor who's come to different conclusions than you?
To your first question, no, that doesn't bother me. It's a technical point that I don't really want to get into because it would take a long time. And as for Ray Nickerson, I want to spend some time talking to Ray and find out why he feels the way he did. I can't answer his different conclusion in absentia. Yeah.
There seems to me to be, with all due respect, a problem. Potential problem with what you're suggesting. And the problem, I believe, is present in our field. If you rely on, in essence, description of the data, the way you're suggesting, the author of the paper uses his or her description to make conclusions in the results and discussion sections. The problem is the Rorschach problem. In fact, different people look at the data differently, but what's printed in the discussion is a result, a conclusion. And that's what gets transmitted through the literature. And so the absence of any agreed intersubject, across-group agreed upon way of coming to conclusions is a potential problem. Where I see it is in JAD, for example, where you, in essence, have a group design. You have 3 animals in one group and 3 animals in another group. You do not do hypothesis testing. And you often come to a subjective conclusion based on your interpretation of the data.
You know, I agree with you absolutely. That's going to have problems. The subjectivity is a problem. I'm certainly not saying that it's better to have subjectivity than not have subjectivity. The question is, how are we going to deal with it? And as I've said a couple of times, I believe that it's better to just present it up front and let people argue about it than maintain this illusion that we've dealt with it when we really haven't. Subjectivity is not going to go away. It's always going to be there forever and ever in science, in all branches of science. And, you know, we just got to figure out the least bad way of dealing with it. Yeah.
Let me start by saying that I totally agree with all of the criticisms that you made about louder hypothesis.
He agrees with all the criticisms. Thanks that I've made. Now, isn't time up?
Now I'm going to say something like Geoffrey lynched here, which is namely to try to sort of construct a defense for why you might want to use hypothesis testing in some cases. So imagine if you've got a very straightforward experiment, just 2 groups, group A and group B. We've got a theory which is predicting that the average score for group B should be greater than the average for group A. So after the end of your experiment, you're going to have to make a decision whether or not you actually got a difference between those 2 groups. Now, if you just plot means with the confidence intervals and you sort of eyeball it, if you've got huge amounts of power and the confidence intervals are very small as a proportion of the difference, then sure, you don't need to perform any kind of test. But aren't there some cases where you would basically be making a judgment about how wide the error bars are relative to the difference between the means? And once you start looking at that, basically you're looking at the obtained p-value.
Yeah, sorry.
Okay. So if you're looking at the obtained p-value, say that there are at least some cases where you want to report that as a useful piece of information for the people to have. And if that is useful for your decision, then aren't we talking about hypothesis testing just in a different route?
Sure. I mean, obviously, the situation that you've described and hypothesis testing are closely related to one another. And by the way, what I would do in that, my main take-home, sorry? Oh, sure. Okay, so the whole question? So essentially the question is, suppose you have two groups. So you have two means, two sample means, confidence intervals around both. You're going to eyeball the confidence intervals and make a conclusion. Do they overlap? Do they not overlap? Questions like that you will be asking yourself. And isn't that really kind of like doing hypothesis testing, except in not as precise a way? So the first answer to my question is that the main take-home message that I provide from such an experiment is not the two means themselves with the confidence intervals, although those would be fine to present. Rather, I take the mean difference and report that with a confidence interval around it. Now you're very close to hypothesis. Now you have much the same information as you have in hypothesis testing. If you're planning to do a two-tailed test, for example, then if the confidence interval includes 0, it's equivalent to being statistically significant, and if it's not, it's not. So in that sense, they both convey exactly the same information. I guess my point and my taste and my subjective judgment is that presenting the mean difference with the confidence interval simply provides a lot more intuitive information about what the data mean than making this artificial dichotomy into significant or not significant. As I said earlier, the significant, not significant dichotomy always has the danger of the not significant conclusion driving the mean difference in readers' minds to 0, whereas presenting it with a confidence interval, you can say, okay, well, this includes 0, but just a little bit, but it also includes this very big mean difference up here. So it simply provides you with a lot more information, and in my mind, a lot stronger intuition about what message you should really take from the data than would the artificial dichotomy of it's significant, it's not significant. Well, it's not in the inverse of that. It's not an estimate of reliability. That's absolutely, yeah. The question, or actually the assertion, with which I agree completely, is that I've been sort of, I and you have been sort of misleading ourselves by saying that statistically, what did you say? How did you phrase it again? You did much. Statistically significant result, that means there is. Oh, a statistically significant result means there is an effect. Right. This is a problem that occurs under many guises. It occurs under the guise of the null hypothesis is never really true. It appears under the guise of, if you get one effect, to what degree do you expect to replicate the effect in a new experiment, and on and on and on. And yeah, I mean, if I'd had a 2-hour talk rather than a 1-hour talk, I probably would have gone through all of those things.
That's the basis of Alan's question. He assumes that if he does the statistical test, it gives him a real answer.
Is that true? Do you really believe that?
It gives one an objective metric rather than a subjective evaluation.
Objective, yes. That's true. But so what? I mean, it would be an objective metric to, reject the null hypothesis if you collect your data on an odd day of the month and fail to reject it if you collect it on an even day of the month. It would be perfectly objective, same rules for everybody, but obviously it would be a totally stupid decision rule. And, possibly the decision rules we have aren't quite that dumb, but they're pretty bad, in my view.
We have time for one last question.
Is it always useful to plot error bars, particularly in situations where you've got a within-subject design?
Oh, I'm happy to tell you that one of those references that flashed by was on how to deal with that very issue. Mike Masson and I wrote an article called Confidence Intervals in Within Subjects Designs. And I'd be more than happy to show you the download site for that that article if you'd like. Just send me an email.
If you could send those references to me, then we could post them if you're willing to do that.
Go ahead. Absolutely. Yeah. Could you remind me, Peter? Just send me a little note. Okay, thanks. Well, thanks. It's been a blast.